In the summer of 1940, when Britain stood on the brink of annihilation, the fate of all Europe was not decided by generals, nor by guns, but by 3 spinning aluminum blades at the nose of a Spitfire. In that moment, high above the skies of Britain, history quietly shifted course. Just weeks after the fall of France, with German forces in control of the continent, Nazi Germany's air force, the Luftwaffe, was preparing a final devastating blow to subdue the last remaining island nation. At coastal air bases, British pilots waited in despair for orders to take off. Their aircraft were too slow to climb and intercept the bomber formations crossing the English Channel. But at a small airfield named Hornchurch, a daring experiment was underway. 2 identical Spitfires, same engines, same pilot, differing only in the 3 aluminum alloy propeller blades made by Americans. And it was that seemingly small difference that gave Britain what the rest of the world was losing: time to fight and a chance to survive. In June 1940, on the runway at Hornchurch Base, 2 Supermarine Spitfire MKs stood side by side. Same airframe, same 1,030 horsepower Rolls-Royce Merlin engine, same 8 Browning wing-mounted guns, and the same pilot, Squadron Leader Desmond Cook, 27 years old, commander of No. 65 Squadron, a man who had witnessed the fall of France and now prepared for the battle he knew would decide the fate of the United Kingdom. In the first Spitfire, everything was as before. A standard de Havilland 2-position propeller, once considered the pinnacle of technology. The pilot had to manually choose between 2 settings: fine pitch for rapid takeoff and coarse pitch to save fuel during cruising. But the second aircraft, assembled just the night before, carried something no one in Britain yet trusted: an automatic variable pitch propeller under license from the Hamilton Standard Propeller Corporation, an American company founded by engineer Frank Walker Caldwell. None of the mechanics at Hornchurch fully understood how it worked, only that the Americans claimed it could automatically adjust blade angles in flight, allowing the engine to maintain peak performance at any altitude, a claim most British engineers at the time dismissed as mechanical fantasy. Desmond Cook didn't have time for doubt. He fired up the first aircraft. The Merlin roared to life, shaking the air. The plane accelerated, lifted off after 320 yards, and sluggishly climbed to 20,000 feet in 11 minutes and 8 seconds, just like every time before. Cook landed, said nothing, and switched to the second Spitfire. As the Hamilton Standard's aluminum blades began to spin, the engine sounded noticeably different, smoother, steadier, and full of pull. The aircraft lifted off the runway. In 1932, on the other side of the Atlantic, in a test workshop of Hamilton Standard Propeller Corporation in East Hartford, Connecticut, the roar of the engine drowned even the wind and snow outside. Amid the smell of oil and metal vapor, a thin man with steel-rimmed glasses held a clipboard. His name was Frank Walker Caldwell, aged 43, a mechanical engineer who graduated from the Massachusetts Institute of Technology, MIT, a man who trusted data more than advice. In front of him, on a steel test stand, an aluminium alloy propeller was spinning at more than 2,400 RPM. Each rotation was a mechanical challenge, because the blade could change its pitch while spinning. In the American aviation industry at that time, that was deemed impossible. Engineers believed no mechanism could be added to such a fast-moving component without tearing itself apart. But Caldwell believed his calculations were correct. He knew that a fixed-pitch propeller, the kind most civilian and military aircraft then used, operated efficiently only in one flight condition. At takeoff, the blade needed a fine pitch for fast rotation and large thrust. But when climbing to altitude, the same pitch created enormous drag, overloading the engine. Thus, pilots with the same aircraft had to accept either weak takeoff performance or slow cruising at height. Caldwell realized if the blade pitch could adjust with airspeed, the engine could always run at optimal power. He had experimented with this idea since the late 1920s while working for the U.S. Army Air Corps, but was considered merely theorizing. The technical reports of the Corps then declared the hydraulic mechanism too complex, too failure-prone, and unable to endure the cold at high altitude. Even Charles Lindbergh, icon of American aviation, once told him at Wright Field, "Good idea, but not worth risking the pilot's life." Caldwell didn't argue. He simply said one line, "Let the data answer." In the Hamilton Standard Laboratory, he and his engineers built the first prototype, 3-blade aluminum propeller, diameter 3.2 meters, with a hydraulic governor using the engine oil to adjust blade angle. The system was fully automatic. When engine speed increased, centrifugal force triggered an oil valve, changing blade angle to reduce RPM. When the aircraft slowed, oil flowed back, angle narrowed to increase thrust. That was the principle of the constant speed propeller. The theory sounded simple, but in 1932, no company anywhere in the world had achieved it. The aviation community called Caldwell's invention the impossible propeller. Just then, opportunity arrived. In early 1933, at Boeing Field, Seattle, the Boeing Model 247, the most advanced twin-engine airliner in the United States, hit a problem. At an altitude of 5,280 ft in Denver, it couldn't climb over the Rocky Mountains. The engine was powerful enough, but the fixed-pitch wooden propellers held it back. Pan American Airways gave Boeing an ultimatum: fix the problem or lose the order to Douglas Aircraft Company. The U.S. aviation industry was shaken. When the phone rang in Hamilton Standard's office, Caldwell understood. This was his chance to prove himself. He had his variable pitch propeller fitted to a Model 247. Test pilot Eddie Allen, known for his calm in all situations, was assigned. On the morning of February 15, 1933, the aircraft took off from Denver Municipal Airport. Everyone waited silently on the ground. The plane climbed beyond 6,000 ft, then 10,000 ft, then soared over the Rockies above 20,000 ft, where, 2 weeks earlier, another of the same type had turned back. On landing in Salt Lake City, Eddie Allen said simply, "The propeller self-adjusts." Perfect! The test report to Boeing recorded: cruise speed up by 9 mph, fuel consumption down by 12%, service ceiling from 12,000 ft to over 20,000 fosin, numbers that no one could dispute. That evening, a telegram from United Airlines to Hamilton Standard. Constant speed propeller exceeded all expectations. Recommend install fleet-wide. Caldwell had won. His propeller, once dismissed as too complex to work, now became the gold standard for every U.S. airline. Later that year, the Collier Trophy for 1933 was awarded for the outstanding development of the controllable pitch propeller, with special credit to Frank W. Caldwell. The President Franklin D. Roosevelt personally handed him the medal at the White House. Caldwell stood there silently receiving the bronze medal. For him, the greatest reward wasn't fame, but that the numbers had beaten prejudice. He realized that his invention was only beginning. Beyond, the world was shifting. In Germany, Adolf Hitler had just come to power. In Japan, the military took Manchuria. Caldwell looked at the map on his workshop wall, red dots spreading across the Pacific. And he knew. The propeller that just saved civil aviation was about to become a weapon that would change the war. In the years 1934, America was still shrouded in the shadow of the Great Depression, but among the factory blocks in East Hartford, Connecticut, the sound of metal and engines roaring inside the test shop of Hamilton Standard Propeller Corporation signaled something far greater: the dawn of an era of speed and power. After receiving the prestigious Collier Trophy for his invention of the automatic constant speed propeller, Frank Walker Caldwell became a well-known name in American aviation. But to him, fame was never the goal. He believed every invention only held value when proven by real-world numbers. And the harshest reality of all was war. Caldwell launched a series of grueling trials he called the Whirl Test, extreme rotational testing. In test chambers, aluminum alloy propellers were spun at 2,700 RPM, undergoing hundreds of hours of operation in temperatures ranging from 40 to 160 degrees. If a propeller could survive that, it could survive any sky on Earth. It was during this process that Caldwell perfected the legendary design, the hydromatic propeller, a mechanical hydraulic system capable of automatically adjusting blade pitch using engine oil pressure. Inside the propeller's hub was a piston controlling a finely tuned gear system connected to a governor no bigger than a coffee can. This structure allowed the engine to maintain constant RPM regardless of altitude or flight speed. Test results showed far greater performance than expected. Takeoff distance was reduced by 30%, climb rate increased by 40%, and service ceiling rose by 6,000 feet. Fuel consumption dropped by 12 to 15%, figures that were indisputable. In March 1934, the U.S. Army Air Corps conducted a direct comparison between two Boeing P-26A pea shooters at Wright Field, Ohio. One with a fixed-pitch propeller, the other fitted with Caldwell's constant speed system. The results stunned everyone. The stock P-26 reached a top speed of 187 mph, while the hydromatic-equipped model hit 203. Time to climb to 10,000 feet dropped from 8 minutes 30 seconds to just 5 minutes 40 seconds. Service ceiling increased from 28,000 feet to 34,500 feet. Lieutenant Colonel Carl Spaatz, who would later command all U.S. Air Forces in Europe, wrote in the test report, "The advantage of the constant speed propeller is absolute. Any force lacking this technology will fall behind in the skies." That single statement changed Hamilton Standard's fate. Contracts began pouring in from the Army, Navy, and even commercial airlines. Caldwell practically lived at the factory, oil-stained coat, fogged glasses, clipboard in hand. He inspected every shipment, checking tolerances down to 1/10,000th of an inch. "A single crack in an oil valve could kill a pilot," he told his engineers. By 1936, Hamilton Standard's production output had tripled. Each hydromatic propeller consisted of 47 precision-machined components, assembled by the most skilled mechanics in the country. Real-world performance kept proving its worth. 30% shorter takeoff roll, 40% faster climb rate, 15% less fuel burn, data that could not be argued, in true American style, accurate, pragmatic, and powerful. In 1937, as Nazi Germany began rearming and Japan expanded its war in China, the U.S. War Department knew it had to be ready. Caldwell was asked to develop a special version of the propeller for the Navy, one that could resist corrosion and withstand sudden temperature shifts on aircraft carriers. He coated the aluminum surfaces with a nickel alloy, boosting durability by 50%. In salt spray tests lasting 500 hours, not a single blade showed significant damage. The Navy immediately signed on. That same year, the first Curtiss P-36 Hawk fitted with the hydromatic propeller took flight. In tests, the fighter reached 323 mph and climbed 40% faster than previous versions. The Air Corps ordered 200 units immediately. By 1938, Hamilton Standard was no longer a small company in Connecticut. It was the beating heart of American aviation. Caldwell reorganized the production lines into a modern industrial layout. Separate blade machining shops, hydraulic units, and test facilities, all running 24 hours a day. On the wall of his office, one phrase hung alone: "Numbers don't lie." Then came September 1939. Germany invaded Poland. World War broke out. Though the U.S. had yet to enter, its factories were preparing. Caldwell received a request from the War Department. develop a propeller that could operate reliably at 40,000 feet, where air was thin and oil could freeze. He and his engineers upgraded the governor system, adding dual pressure circuits to ensure function in all conditions. In test flights at Wright Field, the Wright Cyclone engine of the B-17 Flying Fortress held steady at 2,400 RPM, even at extreme altitudes. Watching the plane vanish into the clouds, Caldwell simply said, "That's what happens when data learns to fly." By year's end, over 800 workers were operating in 3 shifts daily at the East Hartford plant. Endless freight trains carried hundreds of propellers across the country, to Boeing, Lockheed, Douglas. Caldwell stood watching the trains depart into the snowy December night, condensation fogging his glasses. He knew the world was heading into a storm. And when it came, those blades of aluminum and oil would decide who ruled the skies. In 1940, as war engulfed Europe, America still stood on the sidelines, but its factories were waking up. Inside the Hamilton Standard plant in East Hartford, the hammering, the lathes, the roar of test engines merged like the heartbeat of a giant machine. At the center of it all stood Frank Walker Caldwell, the man who had turned formulas on paper into a strategic weapon of a nation. His invention, the automatic constant-speed propeller known as the hydromatic, was no longer just a technical device. It had become a tool that determined speed, range, and the survival chances of every pilot. As the Royal Air Force struggled against the Luftwaffe in the Battle of Britain, the first British Spitfires were equipped with constant-speed propellers manufactured by de Havilland under license from Hamilton Standard. The results exceeded all predictions. Time to climb to 20,000 feet dropped by nearly 4 minutes. Service ceiling increased by 7,000 feet, and climb rate rose by 40%. In war, 4 minutes can be the difference between life and death. The American propeller gave Britain a fighting edge. When news of the victory in the skies above London reached him, Caldwell simply said, "They performed exactly as the numbers promised." But back home, the U.S. was preparing for the greatest war in its history. After Pearl Harbor, December 7, 1941, the peace vanished. From Washington to California, every factory was mobilized. Hamilton Standard was ordered to begin mass production of propellers for the Army Air Forces and the Navy. Caldwell and his team worked non-stop, 3 shifts a day, 7 days a week. From 800 pre-war workers, Hamilton Standard expanded to 22,000, producing 12,000 complete propeller assemblies every month. Each unit contained nearly 50 mechanical components, with tolerances no greater than 1/10,000 of an inch. Companies like Frigidaire, Nash Kelvinator, and Remington Rand, once makers of refrigerators and typewriters, were enlisted as manufacturing partners. That was the strength of American industry, the rapid coordination of millions of hands toward a single goal. Caldwell's propeller appeared on all major American aircraft: the P-51 Mustang, P-47 Thunderbolt, P-38 Lightning, B-17 Flying Fortress, and B-24 Liberator. The performance numbers astonished the world. The P-51 could top 440 mph, climb to 20,000 feet in just 6 minutes, and fly over 1,500 miles. The B-17 could cruise at 30,000 feet, far above the range of most German fighters of the time. Yet amid these triumphs, Caldwell received devastating news. In the fall of 1943, the B-17 Hell's Angels of the 8th Air Force crashed near Schweinfurt, Germany, after its feathering system, designed to streamline propeller blades when an engine failed, jammed due to contaminated hydraulic fluid. The entire crew perished. Caldwell flew to England immediately. He visited every base, spoke directly with surviving engineers and pilots. They told him, "The propellers are brilliant, but in freezing and flak, they need to be tougher." Caldwell returned to Connecticut and started from scratch. He designed a dual feathering system with backup valves and a secondary oil pressure circuit, ensuring blades could lock into position even if the main system failed. He ordered a new test protocol. Each propeller had to run for 500 continuous hours, between 50 degree force and 1 to 140 degree, in a pressure chamber simulating 35,000 feet. No unit would leave the plant unless it passed. Within 6 months, failure rates dropped below 1%, the lowest in aviation history at that time. In 1943, the U.S. Army Air Forces began tracking data. B-17s and B-24s, equipped with the hydromatic propeller, returned to base after engine loss at a rate over 40% higher than those using older designs. In classified reports, General Karl Spaatz wrote, "The constant speed propeller is a technological leap on par with radar. It allows us to fly farther, higher, and faster than any opponent." Standing in the production hall, Caldwell watched hundreds of new B-17s roll off the line, their 4 engines roaring, 12 polished propeller blades glinting under factory lights. He knew that what he had created was not just engineering, it was the heartbeat of American power. Precise, durable, and dependable. By the end of 1943, Hamilton Standard had delivered over 100,000 propellers to the U.S. military and its allies. Caldwell's propeller was now present in every theater of war, from the skies over Britain and France to the vast Pacific. From each turning blade, a permanent truth was etched into history: that intelligence and engineering, forged under responsibility, can alter the fate of the world. By 1944, the war had reached an unprecedented scale. From bases in England, thousands of B-17 flying fortresses and B-24 Liberators of the U.S. Air Force took off daily, carrying tons of bombs toward German territory. At 30,000 feet, 4 roaring Wright Cyclone engines and 16 flawlessly spinning hydromatic propellers kept the aircraft steady in the freezing upper atmosphere. To the Germans, it was the sound of death. To the Americans, it was the pulse of victory. A rhythm powered by the intellect of Frank Walker Caldwell, the engineer who brought laboratory precision to the battlefield. By mid-1944, Hamilton Standard had produced over 300,000 propellers, with an average monthly output of 12,000 units. Each propeller comprised nearly 50 parts, machined to a tolerance of 1/10,000 of an inch. The entire United States had become one vast production line. In Detroit, auto factories cast alloy components. In Ohio, refrigerator maker Frigidaire built hydraulic pistons. In Connecticut, Caldwell and his engineers inspected each tiny governor, no larger than a fist but capable of saving hundreds of lives. That industrial power transformed America into the arsenal of democracy. Caldwell, despite heading the technical division, worked 18 hours a day. He didn't just supervise blueprints, he stood on the production floor, watching each worker, each bolt. When asked why he never rested, he replied simply, "Every turn of a propeller is a life." The results spoke for themselves. The 8th Air Force reported that aircraft equipped with hydromatic propellers had a 45% higher survival rate after engine failure. On the European front, hundreds of crews returned safely thanks to the feathering function, which aligned damaged blades with the airflow to reduce drag. A B-24 pilot wrote in his diary, "We lost 2 engines over Berlin. The propellers feathered, the plane held steady, and we flew 500 more miles back to England." Without the hydromatic, the entire crew would have been dead. That same year, the legendary escort fighter P-51 Mustang was equipped with 4 hydromatic blades. Its top speed reached 440 mph, climbed to 20,000 feet in just 6 minutes, and had a range of over 1,600 miles, enough to escort bombers from England to Berlin and back. The P-51 changed the air war over Europe. Pilots called it the Angel of Speed, while Caldwell simply said, That's what the numbers became. But even at the peak of victory, tragedy struck. In October 1943, a B-17 named Hell's Angels crashed near Schweinfurt when contaminated hydraulic oil jammed the feathering system. Caldwell flew to England to investigate. He spoke with surviving pilots, listening to every detail. Returning to Connecticut, he improved the system, adding backup valves, dual oil circuits, and a new standard. Each propeller had to withstand 500 hours of continuous vibration testing between 50 degrees Wefer and 240. 6 months later, failure rates dropped below 1%, the lowest in aviation history at the time. By early 1945, as Allied forces crossed the Rhine, Caldwell's propellers were everywhere, from Europe to the Pacific. In the skies, the heavy P-47 Thunderbolt could outclimb the Japanese Zero by 40% thanks to its automatic pitch system. At 35,000 feet, where temperatures fell below 60 degrees Celsius, the hydromatic blades kept spinning strong. In every battle, from Normandy to Iwo Jima, the sound of Caldwell's propellers rose with the engines, a metallic drumbeat of freedom. When Germany surrendered in May 1945, followed by Japan in August, the world fell silent. The lights at Hamilton Standard dimmed. In the vast factory, rows of unused propellers stood like monuments to an era that had fulfilled its mission. Caldwell walked through the plant, clipboard in hand, and told the foreman, "Don't stop. Let's carry this spirit into peace." After the war, Hamilton Standard shifted to civilian aviation. The propellers that once escorted B-17s now spun on Douglas DC-4s and Lockheed Constellations, flying passengers across the Atlantic. In a 1946 interview, Caldwell said, "Engineering helped us win the war. Now it will help us connect the world." By the end of 1945, over 500,000 hydromatic propellers had been built. No other American mechanical invention, except radar, had such strategic impact. Caldwell's propeller didn't just help aircraft fly faster and farther. It symbolized the spirit of America, precise, resilient, and relentless. And as he stood by the Connecticut River, watching a DC-4 glide across the blue sky, Caldwell smiled. The propellers hummed steadily, powerfully, no longer the sound of war, but the breath of peace. After the war ended, the world fell into a strange silence. The factories that once blazed with light grew quiet, the engines ceased, and people who had worked 18-hour days began to relearn how to live slowly. Yet in that peace, the propellers of Frank Walker Caldwell kept spinning, not for bombs, but for flights reconnecting a world being reborn. In 1946, Hamilton Standard shifted to civilian aviation. The same technologies that had helped the U.S. Air Force dominate the skies were now installed on the Douglas DC-4, Lockheed Constellation, and Boeing Stratocruiser. On routes linking New York-London, San Francisco-Tokyo, thousands of post-war passengers experienced the smooth, stable flight that only constant-speed propellers could offer. Aircraft maintained steady speeds of 250 mph over thousands of miles, saving fuel and increasing safety, just as Caldwell had once predicted. When the propeller can think for the pilot, the sky becomes safer. In the 1950s, as the jet age began, many thought the era of the propeller was over. But Caldwell knew that before jets ruled the skies, it was propellers that paved the way. He remained hard at work at Hamilton Standard, developing new versions, turboprop and constant-speed turbine propeller, applying hydromatic principles to turboprop engines. Aircraft like the Lockheed P-3 Orion and C-130 Hercules used technology directly descended from his designs, operating at altitudes of 30,000 feet and speeds over 350 meters per hour. And many still fly well into the 21st century. Caldwell wasn't just an engineer. He was a mentor to a generation of American technicians. He taught them to think in numbers, to question before deciding, and to find beauty in machinery. One young engineer said, "He never talked about glory. He only talked about precision." In his small East Hartford office, Caldwell kept a photo of Spitfire K9847, the first British aircraft fitted with a constant speed propeller. Beneath it, he had written just one line: "Proof in the sky." In 1948, Caldwell retired after more than 30 years of service. He received dozens of honors, including the Collier Trophy and a commendation from President Roosevelt. But what he valued most were the letters from pilots around the world sent to Hamilton Standard. One American pilot wrote, "You didn't just save our lives, you gave us the right to come home." By the mid-20th century, the hydromatic propeller was installed on over 90% of the world's propeller-driven aircraft. It was more than a feat of engineering. It was a symbol of an era when people believed that with intellect and hands, they could conquer any limit. At NASA, Caldwell's automatic pitch principles were later used in rocket booster blades and atmospheric research aircraft. From the aluminum blades over Essex in the summer of 1940 to the jet engines of spaceflight 30 years later, a single invisible thread connected them all: Frank Caldwell's pursuit of perfection. In February 1974, Caldwell passed away in Connecticut at the age of 85. In his eulogy, the director of Hamilton Standard said, "He didn't just invent the propeller, he invented a way of thinking, that no detail is too small to be made perfect." His name was etched into the National Air and Space Museum in Washington, D.C., alongside icons like the Wright brothers and Charles Lindbergh. Today, whenever an aircraft takes off, jet or propeller, Caldwell's principles are still at work. When a pilot advances the throttle, an automatic system adjusts blade or turbine pitch to maintain optimal RPM, power, and fuel efficiency. Beneath modern alloy casings lies an idea born on a cold winter morning in 1932. Let the machine adapt instead of forcing the human to control it. In today's skies, where sunlight reflects off thousands of spinning blades, Caldwell's legacy still shines. It is not just an invention, it's proof of an era when America believed in the power of intellect and labor. A time when engineers, mechanics, and pilots proved that victory doesn't come from weapons alone, but from the perfect revolutions of those who believe in what's right. And as the engine fades into the sunset, we can still hear the echo of history, the hydromatic propeller spinning on, breathing life into a world upheld by those who dared to dream, dared to build, and dared to believe that engineering could save humanity from its own destruction.